So, hello everybody. So like I said in the chat, since today's our last class, it'd be nice to see you. If you want, if you know, obviously, if you're uncomfortable, keep your camera off. But if you don't mind, turn your camera on. And then if the internet crashes, we'll go back to not seeing each other. But at least we can wave each other hi. It's good to see everybody. Hello. I have posted the final exam. I hope you've all found it by now. And a couple things I want to say. One is that we can talk about it today if you want, and we can also talk about it, after today. So if you feel like you'd like to have like another meeting, later in the week or early next week before the exam is due and talk about it more, let's have a discussion and find a time that might work, and I'm happy to give extra time. Okay. Cool. So any questions about anything? So today I did not prepare a class. I just want to answer questions and help out where help is needed.
I mean,
I have, oh, Berkeley, if you have one.
Okay, I was just gonna say, start from the top and like go through the questions on the final, and like if anyone has questions on it, that was my plan or what I had prepared, or is any questions I had on those.
I do have a specific one about number 2.
Mm-hmm.
So I just want to make sure I'm understanding the relation correctly. Let me just.
So let me share the screen for a second and pull the exam out so we can all look at it together. Okay. So question 2, you said, Tyler?
Yeah, or the definition of the of tilde. Right above.
Yeah.
So when we say that if P of t is similar to Q of t, if and only if Q of t minus P of t is equal to t squared plus 1 times S of t.
Mm-hmm.
The first part of question 2 asks us to find 2 polynomials that are not equivalent.
Yeah.
And right now I'm struggling with this, and I just wanted to make sure that I'm understanding this correctly, because when I pick 2 polynomials, I get, even no matter what the difference between the Q of t and the P of t is, I can always divide by t squared plus 1 and have ns of t that is still within the realm of r of t.
Right, but here it's asking to have no remainder.
Oh, does it say no remainder?
Well, it doesn't say, but there's not a remainder here, right?
Okay.
Because, so the one thing I want to strike, this is very similar to what we did with the integers, right?
Okay.
When we said that an integer m and an integer n are equivalent if and only if their difference is a multiple of 9, right?
Okay.
Obviously, you can divide any integer you want by 9, and then if that integer is not a multiple of 9, you will have a remainder which is a number between 1 and 8, right? And similar for polynomials, you can divide q of t minus p of t by t squared minus 1, which is a polynomial of degree 2, right? And if it's not divisible, then the equation on the right here would not end here, but it would have a remainder, which is a polynomial of degree 1. Right?
Okay, that makes a lot of sense. I was trying to come up with like a sideways parabola equation where it wasn't actually a function. I couldn't figure out how to break that.
Yeah. No, the thing is, again, you should think of really polynomials is the same as integers, right? And so, yeah, you can always divide 2 integers, but you get a fraction in general. It's only a special circumstance. So you can always divide 2 polynomials, but you don't always get a polynomial.
Okay, thank you.
Okay. Cool. That's great. Great question.
So talking on number 2 as well.
Sorry?
This is also on number 2. I was a little bit confused about the relationship between P of t, Q of t, and S of t. Like, are these numbers or functions?
No,
like, I'm
these
just
are polynomials.
About what's going on with those 3.
Yeah, so these are polynomials, right? So let me write something so maybe it can remain right. So what we did in our unit 9 is our number system. Z was our initial number system. Number system, right? And so we had an equivalence relation defined as two integers m and n are equivalent if and only if their difference is a multiple of 9. 9k, and here you see the important thing is that I didn't say k is just any number, but k is an integer. Right? K is not allowed to be a fraction. Right? So for example, right, if the number 20 and the number 10 walk up to you and they ask you, are we equivalent? Right? How do you decide that? You say, to decide that, you say, okay, let's see, 20 minus 10 is equal to 10. And 10 is not divisible by 9, right? 10 is equal to 9 times 1 plus a remainder of 1. Right? So the fact that there is this remainder, right, that you see is not here, tells you that no, 20 and 10 are not equivalent. Okay? Now you're supposed to, now how are we changing our situation? We're replacing the integers with polynomials. Right? But the condition is the same, right? Is that P of t is equivalent to Q of t if and only if their difference, P of t minus Q of t, is divisible as a polynomial by this polynomial that I chose, x squared plus 1. Which means that if you perform division, you get a polynomial, s of t, and no remainder. Zero remainder. Okay? And so, oh, sorry, and I switched from t to x. There's no x. T squared plus 1, right? So at this point, you know, two polynomials can walk up to you, something like, you know, t cubed plus t plus 23, and t to the 27 can walk up to you and can ask you, are we equivalent? Right? And then how do you check it? Well, you have to take the difference of the two, t to the 27 minus t cubed plus t plus 23, and you have to do polynomial division by t squared plus 1, right? This whole thing. And then if you get a remainder, then that's bad. It means that these two things are not equivalent. And if you don't get a remainder, then they're equivalent. Okay. Of course, I encourage you to not pick examples, you know, as examples, polynomial of 27th degree, right? Because you're not, you know, keep the example simple so that you also don't risk to do any kind of computation mistake, right? Did that help, Berkeley?
Yeah, that helped a lot. And
Okay.
we only have to find definitions here. We don't have to prove, right?
Right. So the definition is given to you right here. Let me see. This is the, oops, let me wipe this. But this is the definition, right? So when you want an example of two polynomials that are equivalent, right, you want two polynomials that make this statement true. And when you want two polynomials that are not equivalent, you want this statement to be true. That means that they have to make this statement false. Okay, because this right here that I'm boxing right now is the passport, right, for the document that tells you what it means to be equivalent in this exam. Cool. So should we scroll on the exam and see if there's anything else that needs to be clarified? It's not, my goal in writing this exam is not to trick you, right? Is to challenge you, right? So anything that is not clear, like I'm gonna want it to make it clear, right? So that's
So for number 1, I was a little bit confused about what would not be a polynomial in T with real coefficients.
well, again, so there is a definition here, right? Let me pull this thing out again and wipe this. Right? In this case, the definition of a polynomial is right here. Right? So something which is not a polynomial is something that does not satisfy this definition. Right? You're not supposed to remember what a polynomial is from previous lives, right? I mean, of course, even though you do, right? But you're just supposed to use this definition. Right? So that first question is just, to test that you know how to read and use a definition.
Okay, so this is like simple breaks of this pattern, right?
What, sorry, say it again.
This, like, you could break this with like really simple things, right?
Oh, absolutely. Yeah.
Okay.
Yeah. You only have to be careful that if you're thinking that you're breaking with something so simple that it ends up being a very special case of this definition, right? But you can certainly break it with something very simple.
Okay.
Okay. Cool. Okay, let me then go down and scroll. Okay, so I want to point out question 3, right? This has nothing to do with this particular equivalence relation, right? It's just asking you for a definition that we have talked about in Unit 9, right? And it's just about everybody being able to like look back at your notes and show me that you have understood Unit 9.
So will this be a definition that we defined or a definition that was within the book, or is it something we'll have to define?
No, so this is something, the definition of an equivalence relation being compatible with operation, addition, and multiplication is something that we've talked about in Unit 9, right? This is not something that you have to invent, right? But this is talked in Unit 9.
And we get to pick the set X and the equivalence relation?
No, so I mean, so given any set X that has addition and multiplication, right? You should be able to tell me what does it mean for an equivalence relation on X to be compatible with addition and multiplication. For any X, you don't have to choose a specific X, right?
Okay, that makes sense.
Yeah. Cool. Whereas in question 4, now we're saying, okay, you wrote down a definition in problem 3. Now zoom in into this particular set, being X is polynomials in T, and the equivalence relation is defined here. Now show me that this equivalence relation on polynomials is compatible with addition and multiplication of polynomials.
Can I ask a quick question about that?
Yeah, absolutely.
So I believe we did this in, oh man, I can't remember if it was 8 or 9, but this is kind of the idea where we're saying like if x1 is equivalent to an x2 and y1 is equivalent to y2, in the previous example, we said, oh, their difference is 5 times an integer.
Mm-hmm.
And the way we showed that was kind of using algebraic manipulation to show that those two were the same. And so it's kind of the same idea here.
It's going to be extremely similar. Yeah. If if you understood well what we're doing in Unit 9 with integers, really a lot of this is replacing the number system that is given by integers with this different, slightly more abstract one, which is polynomials.
Okay.
But you're
Sweet. Thank you.
absolutely right. It's going to be, you know, essentially the same proofs where you replace your integers with polynomials, and then you observe that the algebra of integer and the algebra of polynomials is very, very similar.
Okay.
You can multiply, you can divide, there's remainders, and yada, yada, yada. Yeah, absolutely.
Okay. Sweet.
Cool. Right, and so similarly, this addition and multiplication with a box is, again, exactly the same as what we did with integers, except that now we have polynomials, right? And you're gonna add two equivalence classes by just adding the polynomials and then taking the equivalence class. That's the definition, okay? Great. So again, question 5, right, is about, you know, showing, you know, algebra with equivalence classes, right? So you can apply, first of all, these two definitions right here that I'm highlighting, right? And the fact that we said, you know, we proved in class a theorem that the number, when you have an equivalence relation which is compatible with addition and multiplication, then the quotient set becomes a number system. So you can use that to actually say, well, then that means that I can do algebra the usual way, right? I can add, I can distribute, and yada, yada, yada. But if you use this definition, right, you might not end up with something that looks on the nose. Let me wipe it here. You might not end up on the nose with something that looks like 0 equals 0, right? You might end, you know, you might, if you're very lucky, but you might end up with something that looks like t to the 48 plus 49t to the 46 plus blah, blah, blah equals 0, right? And this does not yet mean that this equation is false, right? Because we have square brackets around this two terms, being equal means that the two polynomials are equivalent, right? So what you have to do is say, okay, well, if I did the algebra here and I did not come up with 0 equals 0 with the square brackets around it, are the things within the square brackets equivalent? And again, you have to go back to the definition of what it means to be equivalent and work it out.
So on number 5, we would have to prove those two statements above, the addition and multiplication, before we could work with.
No, I'm not asking you to prove that. That is already, we did that in class and you can use it, right? So things that I'm not asking you to do here, right? I'm not asking you to check that this is an equivalence relation, right? I'm not asking you that this rule satisfies reflexive, symmetric, and transitive, right? You can give it for granted. I take responsibility that I gave you a good equivalence relation. And I'm not asking you to reprove the theorem that we proved in class that says that if you have an equivalence relation on a number system compatible with addition or multiplication, then the quotient set becomes a number system. You don't have to reprove it, you can just use it, right? And the way that this number system on the quotient set works is explained by these two definitions. Okay, and again, this is, let me, oops, not this one. Let me pull out this again real quick and draw the analogy with integers. If I can. So it gives me any more space down here? No? Okay. Come on. Microsoft. Just open a new page. Okay. Really? Okay, there we go. Now I can move it. So with integers, right, we have that if we're in Z mod 9Z, right? Then 5 box plus 7 is equal to the equivalence class of 5 plus 7, which is the equivalence class of 12. And then if we want, we say, well, we like to call the elements of Z mod Z the numbers 0 to 8. Then you can say, okay, well, this is the same thing as the equivalence class of 3. Okay. So this is what happens for integers. We're going to do exactly the same with polynomials. Okay. Oops.
So is number 6 building on unit 5?
So I don't remember. What was unit 5? So I guess the answer is probably not, if I don't remember. But number 6 is building again. It's only actually really using this definition number 2. Right? It's using definition number 2, but it's also using, well, it's using some of the things that you've done before, right? So we have right here a question that says, well, is t squared and the number -1, are they related somehow, right? And then you have the fact that you can do algebra with these things, right? So in particular, what I wanted to do is this. Yep. So in particular, say that you showed that t squared is equal to 47 for some reason. This is not true, but imagine you showed this, right? Then, well, t to the 4th, right? Well, t to the 4th is t squared times t squared. Sorry, t squared times t squared. But this is the equivalence class of t squared times the equivalence class of t squared, right? And so if now you have shown that t squared is 47, well, I mean, you can very well replace this with 47 times 47. And eventually say, okay, t to the 4th is the equivalence class of 47 squared. Right? So you can do this, and sorry, I got lazy. You should really put a box times here, right? And here, because you're multiplying equivalence classes. But what this exercise here is trying to get you to do is to get comfortable with doing algebra on this quotient set, but using the fact that equivalence classes might have different names. And so if you have 2 different names for the same equivalence class, you are absolutely allowed to simplify your life by replacing a more complicated name with a simpler name. Okay? Just how, again, going back to the analogy of integers, right? If you're in Z mod Z, oops, let me pull this out again. What I want is wipe. In Z mod Z, right? If you have the number, 100,000, you're like, well, geez, this is 999 plus 1, so this is the same as 1, right? So any computation that you have that involves the number 100,000 in Z mod Z, you can just replace that with 1. And that a lot of times makes your life easier. Okay, great. Any questions on number 7? Is it clear what question 7 is asking? I'm hearing no yeses and no nos. Is it clear? Is it confusing? So what's the analogy in Zmod 9z of question 7? Pull it out here.
So I haven't thought about this one too much yet,
Mhm.
but it seems to me that there's something to do with every degree of a polynomial is equivalent to I don't know how to phrase this. Those are important, and that's where I'm at right now. I don't know how yet, but
Okay, so let me say, because I don't want to give out too much for this problem, but the analogy with Zmod 9z, right, is that if we take just number from 0 to 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, right, you can find a bijection. There exists a bijection between the set of numbers 0 to 8 and Zmod 9z. Right? How is this bijection going to work? Well, it's pretty simple, because to the number n, you can associate the equivalence class of n. Right? And so this gives me a function from this set to this set. Okay? Now, in order to show that this function is a bijection, well, you have a few different options, right? So to show a function is a bijection, what can you do? There's at least 2 different options that I can think of.
You show that the function is both surjective and injective.
Yeah, so one way is like take the definition of bijective means injective and surjective, right? One is show it's injective and surjective, which means pick out the definition of being injective, being surjective, and show that those definitions apply in this situation. And can anybody think of another way? Which is a little bit more sneaky, but sometimes it's very nice.
Is it that you can form a bijection with the set of all reals?
No, in this case, it's 2 sets that I am putting in bijection, right? They have 9 elements, right? So certainly you would not expect to put them in bijection with all reals, right? But one thing that bijections, one property that bijections have, so let me draw an example of a bijection, right? If I give a function, I'm giving a direction of my arrows, right? This is a function from x to y. But if it's a bijection, what can I do with these arrows?
reverse them.
I can reverse them, right? And this is only true if it's a bijection, right? If something is not a bijection and you reverse the arrows, then the thing that you get is no longer a function, right? So the other thing that you can do is you can show that it is invertible. And how do you show that it's invertible? Well, you construct an inverse function, right? And remember the definition of invertible, right? F is invertible if there exists a G such that F composed with G and G composed with F are both the identity function. This is the identity function X and this is the identity function of Y. Right? And so F is going this way and G is going this way. Okay, so you don't have to do them both, right? You can choose the one that you feel you're able to do and explain better, right? But these are two options to show that there's a bijection between this set that I gave you right here, Q, and the quotient set of polynomials via the equivalence relation. Right? And notice the analogy, right? This is a subset of all polynomials, just the same way that 0 to 8 is a subset of all integers, right? But what works in here is that with this subset 0 to 8, you end up catching each equivalence class in Z mod 9Z exactly once, right? You catch all equivalence classes, and no two of these numbers between 0 and 8 are equivalent themselves, right? Because if you were to be like, if you added a 9 in here, right, you still have a function, but it's no longer a bijection because 9 and 0 are equivalent, so go to the same element, so it's no longer injected, right? So it's this subset of numbers that I've chosen here is being fine-tuned exactly to pick each of the equivalence classes exactly once. Okay. Yes, no, maybe? Is everybody fairly happy? And sorry, I haven't, I see that now there's chats. I haven't pulled out the chat. Okay. Oh, okay. Thanks for having written the chat in the meantime. Sorry, I wasn't seeing it. McKenna, did I answer your question about definition 2 being used in problem 5 already, or?
Yeah, it's good.
Okay. Thanks. Yeah. Sorry, I wasn't looking at the chat. All right. Let me again just comment a couple things, right? In question 8 is again a question about not specifically about this problem, right? It's a question about theory that we've done in units 6 or 7, right? So it's just about remembering that if you have two functions that are bijective, then their composition is a bijection. Okay, so this is again, it's a question that is not related to this specific problem of polynomials. It's a general theory question. But the reason that I put it here is because I'm hoping that question 8 will help you answer question 9. Okay? This helps. Question 9. And finally, so hopefully question 10 will also be not too confusing, right? But what this is saying, okay, well, I have a bijection, right, that for each of these elements in this quotient set associates to each of these elements a complex number. But this bijection is actually also preserving operations in the sense that we know how to add these polynomials in this quotient set. It's been defined up there, right, by the box plus. And we certainly know how to add complex numbers. And I want you to show that, and sorry, yeah, there's a typo here. I'll fix it. Let me show you what the typo is on here, and then I'll fix it on the exam, and I'll send you the better copy. So this is an addition here, right? And this is an addition of complex numbers. So I want, to have an equality, I really want to have an equality of complex numbers, right? So this is the correct statement, and I'm gonna fix it in the exam and upload a revised copy in the announcements. Okay, because what this is saying is like, okay, you can take two polynomials, add them as polynomials, and then send them over to become a complex number via this bijection, or you can first send each of the polynomials to become a complex number and then add them, and it should be the same thing.
So you've kind of already done this, but can you give us a quick walkthrough of what's going on notationally in number 9?
In number 9?
Yes.
So number 9, I'm asking you to give me a function, right? So basically here you have to tell me, okay, if I have phi of an equivalence class, P of t, this should define a certain complex number, right? So some a plus ib, where a and b must be computed using p, right? So that whatever polynomial you give me, I know what a and b to choose. Okay. And so now the reason, this might seem a little bit weird, right? Because if I give you the polynomial, t to the 23 plus 47t squared plus t squared plus 38, how do you come up with an a and a b, right? But here's where I'm hoping that question 8 can help, right? Because you're supposed to give me a bijection between this quotient set and the complex numbers. And in question 7, you've already given me a bijection between this quotient set and this set Q. Okay, so if you have a bijection from the quotient set R of t modulo the equivalent relation to Q, and this you already have it. And now you can come up in an easier way with a bijection from Q to the complex numbers. If you can do that, if you can do this, then you can just use question 8 and say, okay, well, then the composition of two bijections is the bijection, and you get this, which is what you want. Okay?
What is Q here?
Q is right here. Is this subset of polynomials defined right here. Oops, sorry, I erased everything. We're back here. Okay, so clearly you'll need to spend a little bit of time, right, with unpacking all the information that is in the exam, right? But there's a lot of little steps that you have to put together. There's none of this exam is requiring you like any kind of, you know, extremely sophisticated trick, or, you know, if you don't come up with the brilliant idea, this is no, it's a bunch of like little steps that, you know, are used by like they're made by like using definitions, and but you need to carefully understand the definitions. That's the point. Okay, so let me remember one more time. I'm going to correct it. By tonight, I'll have this corrected, but this is the correct statement. And these are equalities. These are equalities of complex numbers.
So for the ones where on like number 1 and number 2, I don't know, what are the other ones where you have to like just give examples of something that is or is not?
Mm-hmm.
Do you need explanations for all of those? Like to what extent do you need explanations of all of this stuff for the final?
Well, so what I would say is that, you know, when I'm just asking you for an example, you know, I'm asking for an example. You don't really need an explanation, right? If you're asking to prove something, right, then I'm asking for a proof, right? So I think just kind of be careful at reading exactly what the question is asking, right? Here it's really writing just an example in question 1. In question 2, write an example. In the second part of question 2, I'm asking you to explain your answer, right? So a yes and a no is not sufficient. I want you to explain why, right? And what I would say is that, you know, if when you're doing the exam you have a doubt, feel free to, you know, shoot me an email or to put a question on the discussion so that, you know, I can answer it for everybody, because I'm totally happy to clarify anything else. Okay. And so also by show, I really mean prove, right? So maybe I'll change this word so it's even, no, there's no shadow of doubt, right? But showing like a general statement like this is really proving. Okay, and finally, I want to you know, just say a couple things on the second part of the exam. I want this part to be both an opportunity for you to sort of think about what this class was all about, right? Because it's very common, it's very easy when we study something to be like very focused on just the particular task at the moment, right? The homework of this week, right? But I think it would be very valuable for everybody to kind of, you know, step back a little bit and think about, okay, what has gone on in this class? What are the things that, you know, we have learned? What are the things that, you know, the ideas, the big ideas that have been passed on, or that I try to pass on? And so I think that it'll be a good exercise to try and reflect on this. And then the second goal is for you to let me know, you know, how this class worked. And you know, I would be very happy to have any kind of constructive feedback, and so that, you know, future times I teach this class, I can try to like see if I can make it work even better for the next students. So don't be shy. I'm not gonna, you know, I've been in this business long enough that I don't get pissed or offended easily when people are like, oh, I really didn't like this part of the class. I go, well, too bad, so sad. But I mean, you're totally entitled in your opinions. Um, but yeah, so try to put in this answer a little bit of both if you can. Like what, spend some time thinking about what was this all about, what has this been useful for, what were the ideas that were conveyed, and what worked, what didn't, what was good, what was not good, all of that. Cool.
So for this second piece where it's the essay, is this kind of an opportunity to write an informal reflection about the course and how we did with it?
Yeah, you can put that in as well. Yeah. So the only thing that I would ask you not to do is to don't just put like a list of topics, because I know what topics we covered, right? So I don't want an essay which is like, in unit 1 we did this, in unit 2 we did this, in unit 3 we did this. Really like a reflection about what across units and what are the the main ideas that came out, right? For example, starting on unit 6, we really talked a lot about functions, right? So functions was certainly a central idea that we talked about for the second half of the semester. Function is something that you talk about in calculus. How was it different now, right? What have we done now that is done differently in calculus, right? We have certainly taken a point of view which is a little bit more general, a little bit more abstract, right? So these are the kind of things that I would like you to spend some time reflecting and and write informally. It doesn't have to be, I'm not a creative writing teacher, so I'm not going to judge your form other than please write in a way that I can understand what you mean, right? Don't write backwards and from right to left, right? Make it easy for me to read your essay, and other than that, it'll be all good.
So you said that you don't want it to be like a list of like the topics, but what if it was like the other end of the spectrum, and like I just kind of talked how I felt like during the class, and like I could talk about like topics that were hard, but how much do you want us to go in depth into topics versus just?
Yeah, I mean, it's I don't have a rule that I can give you that is very quantitative, right? I would like and I would ask everybody to spend some time thinking about what they what you took out of this class, right? And if that includes saying like, oh, I really enjoyed talking about infinity, and so you talk a little bit about that topic, that's fine, right? So I'm not saying don't put any topic at all. Don't only be like, it's 5 pages of how much I hated doing group work in class. Okay, that's, you can tell me that you hated group work, but don't let it be the only thing that you talk about, okay? So try to, find your own, what you feel is your own balance, but to address a little bit of both.
Okay, that makes sense.
Okay, cool. I guess we're out of time, so it's good to see you today. Actually, I can say that. Hope everybody is doing okay, and do not hesitate to be in touch if you want a little bit more help or clarification. And if there is enough desire for another kind of meeting, we can definitely set it up either in the next couple days, or on Monday or Tuesday morning. I'm gonna certainly be available. Okay. And yeah, I hope this class was interesting and useful and enjoyable. And thank you all for participating. And hopefully we will see each other in person at some point in the future on campus if we're ever able to go back. All right. Take care, everybody.
So,
Thank you, Renzo.
And
Thank you.
yeah, good luck with the exam. Yeah,
Have a good one.
thanks. Take care.